This lecture is about crystallization and the techniques used with the crystallization, which is basically a purification technique. As always, it's always important for you guys to read your textbook, where I might miss something in these lectures, and the book always has a lot of useful information. So, what exactly is a crystal? Well, here you can see a crystal or crystalline solid is a solid material where molecules are arranged in a highly ordered structure, forming crystal lattice. The process of crystal formation via crystal growth is known as crystallization. So you'll see that with solid compounds, you can have them in three different ways, right? So here you have a crystalline compound. You see the order of the crystals here, perfect, like soldiers in a standing in the line, right? Or you can have polycrystalline, which is crystals, but the crystals are arranged in random orders and they're kind of just stuck together. Finally, you have amorphous solid, which is just gunk. Sometimes it's very gooey, depending on how impure it is. Table sugar is sucrose, which is this molecule right here. You may have noticed that there are different kinds of sugar. There's a crystalline sugar, there's a powdered sugar. So when it's more powdered, it's more likely to be amorphous, of course. Amorphous solids can be any kind of random consistency. So here you can see the sugar powder right here. It's probably amorphous. This is, if it's colored like this, but it kind of looks like a crystal, it's likely to be polycrystalline, right? And then sugar crystals are usually white, as most compounds, with some exceptions. When they're in their crystalline form, they're kind of white. Selecting the right solvent is an important thing when doing crystallization. One of the more important things to consider is the polarity of the solvent. Not every organic compound will be soluble in every solvent. So the polarity of the compound depends on the dipole moment of the compound. If you will remember from your general chemistry class, when you have your periodic table here, right? You have, there's a trend going. You have to remember this trend. It's very important. Going from bottom left to top right, you have your increasing electronegativity, right? So when you have something from over here with a compound from, say, further to the left, right, you'll have a more polar bond than if you have just a carbon-carbon bond, right? So the dipole moment of a compound is directly related to the dielectric constant. The dielectric constant of a compound is what determines how polar it is. And it's represented by this epsilon right here, right? A more polar compound is more soluble in a more polar solvent, and a nonpolar compound is more soluble in a nonpolar solvent. Finally, one other important thing to consider is the higher the temperature of the solvent, the more likely a compound is to dissolve in it. Here you can see an example of different kinds of compounds that dissolve in different ways. You can see here there's water, which is a highly polar compound that hydrogen bonds. You'll see that things like benzoic acid and sugars, which are rich in oxygen and hydrogen bonds, are more likely to dissolve in water. If you'll notice, when you put sugar in tea or something, when it's iced tea, it takes forever to dissolve. However, when you heat it up, you'll notice that the sugar dissolves in the tea much quicker. Then there are solvents like dichloromethane, which are polar solvents, but they don't contain hydrogen bonding. You'll see that compounds such as caffeine here, which is a lot of polar bonds between nitrogen and carbon, and also nicotine was the same way. These are more likely to dissolve in the solvents such as dichloromethane. And of course, hexane, if you guys know, have covered or not. Hexane is a six-membered compound, right? And this is more likely to dissolve larger molecules with hydrocarbons chains attached, such as this fatty ester here, right? This large ester. And pretty much as long as they have a lot of carbons and hydrogens, you can use something like hexane as a solvent. Crystallization is a form of purification. About this purification only works with compounds that are solid at room temperature. So you can't really use this technique with liquids or gases. They have their own unique forms of purification. The polarity of the solvent is very important with crystallization. You want to select a solvent that will dissolve your solid at higher temperatures while dissolving the impurities at much, much lower temperatures. For example, here you see water is highly polar solvent. It's good for dissolving benzoic acid, but it only does so if you raise the temperature so that the benzoic acid is dissolved in it. When you do this, you heat up the solution, everything dissolves. Once you cool it down, the first thing that drops out of solution is your desired compound, which would be in this case the benzoic acid here. And all the impurities should ideally remain in solution. You can see here an example of crystallization. You have your solid here with impurities. You pour in your hot solvent and everything dissolves. You should have this heated up to make sure everything is dissolved. Once you do that, you let the crystallization occur by cooling the solution. Then you pass it through a filter. This is usually connected to vacuum, and the liquid is sucked down into the collection flask with all of the impurities in it, and you collect your crystals up here, right there. And these should be more pure than they were before you did the recrystallization. I'll now be going over a specific example of experiment done to recrystallize in the lab. So the first step here is to have a hot gravity filtration of benzoic acid. So I'm just going to read this procedure so that you guys can know what to do. In a 50 milliliter beaker, no larger than 100 milliliters, take around half a gram of impure benzoic acid and add 20 milliliters of water. Heat on a hot plate to dissolve the solid and make a solution. You may have to occasionally add water in 2 to 5 milliliter portions to maintain the volume at around 20 milliliters. This is because when you're heating it, it starts to evaporate. And this is worse with other solvents other than water, which are much more volatile. Do not let the solution dry out, and do not let the solution get concentrated below 10 milliliters. Make sure to control your heating. So on the second beaker, you have another 100 milliliter beaker, add around 25 milliliters of water, and keep it hot or boiling. This is hot water that will be used before and after the gravity filtration that you will be doing shortly. So in a flask, you set up the gravity filtration on the hot plate. Use a 150 milliliter Erlenmeyer flask right here. Then I use other very large size flasks. Just before the actual filtration, soak the paper through thoroughly with some hot water. The reason for this is in order to prevent your compound from recrystallizing on the filter. You want it to be hot while you're filtering it. This first filtration I didn't talk about in the previous slide is actually to eliminate any mechanical impurities, such as, well, an example would be if you had dust or sand in your solution, something that just will never dissolve in water. It'll get filtered out here. Your compound that you want should not be getting stuck in this filter because this should be a hot filtration. All right. So you could do a quick filtration of the benzoic acid. If you observe any premature crystallization on the filter paper, make sure you use your extra hot water and you pour it on there to make sure all the benzoic acid falls through into the next flask. So the next step of this procedure is the crystallization. So here, after the gravity filtration is successfully done, the Erlenmeyer flask contains your benzoic acid solution from which pure benzoic acid crystals will be formed. But in order to make sure that this happens, you have to have the correct amount of volume inside your flask. So you have to make sure you have at least or no more than 25 milliliters inside. Otherwise, the recrystallization might not occur because there's just too much solvent. To gauge the solution volume, you can use the marks on the flask, right? So the solution volume is more than 25 milliliters. You must keep heating the flask on the plate until more of the solvent evaporates, right? So this step is important. Do not skip. Once you reach the desired volume, Take the flask away from the hot plate and let it cool slowly. So at this point, this is when your crystals should start to be forming. In most cases, if you follow the procedure correctly, this should be forming crystals, right? But if you do not observe any crystallization, even when the solution cools to room temperature, then you should cool the Erlenmeyer flask in a bucket of ice water. If this doesn't work, you can also scratch the glass, or you can use a seed crystal. The reason for this is the crystal needs something to grab onto, right? So sometimes these flasks are way too smooth, and there's nothing that'll catalyze the formation of a crystal. So it needs something to grab onto. This is why the scratching of the glass with a spatula is needed, or the seed crystal, which is also functions. The next step in your filtrate and your crystallization is probably the easiest step. However, it requires a lot of careful preparation. For one thing, always, 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 no matter what, even if it's not recrystallization, always clamp everything, because things tend to tip over. But especially you want to clamp this one because it's top heavy. You see here, this is a ceramic funnel, and you don't want to tip the glassware over, okay? So this is clamped. Also, another thing to mention here is this filter paper. You'll see here, this is exactly the same size as the Buchner funnel. Always make sure that's the case. You don't want to have folds here or anything like that. You also don't want to have any of the holes exposed, because then you'll lose product through the holes, right? So you basically, once you have your crystals here, grab your matte flask and you turn on the vacuum. This is a vacuum line right here, right? And you pour in your solution slowly, carefully. Try not to let any of the solution go to the sides of the filter paper. Sometimes they're a little bit too small for these funnels, and they tend to seep around the sides, but generally speaking, you want to have your filter paper the correct size and collect your crystals on that filter paper. Once you do that, you leave it for a good while. It takes a very, very long time to collect these crystals here, right? But once you have them, they should be nice, white, pretty crystals. So the final step in this procedure is a little bit of math. So if you did everything correctly, of course, one thing I forgot to mention in the previous slide is you want to make sure all of the crystals from your Erlenmeyer flask were transferred onto the filter, and you can use a little bit of water to do so. But once everything is dried, completely dry, because there's oftentimes a lot of water left in the filtrate, you want to take the mass of your compound. If you did manage to completely dry your crystals, you want to be careful, because the fume hoods have a lot of air going through them. They're sucking air in to make sure we don't get sick from all the fumes, so they tend to blow the crystals off. Also, be careful when you're carrying them on a watch glass, because they tend to fly off. They're very flaky crystals. You can do your percent recovery here. You should have weighed your sample initially, if I didn't mention that before. And then you take the final weight after you had recrystallized them. You divide it by the initial weight here, and then times 100. And this should give you your percent recovery, right? And as always, please make sure to dispose of all your waste. The benzoic acid and the filter paper, they go in the solid waste. Broken glass, of course, this always happens. I've seen it many times. Always goes in the glass waste. Aqueous waste, such as the water you use for the benzoic acid, it goes in there. And then, of course, as always, please keep the balance area clean. It always becomes a mess. I've seen as a student. And just please don't leave a mess.